Or wormholes. The word itself sounds like something out of science fiction, and for the most part, it is. We see them in movies and TV shows all the time: a shimmering tunnel, a swirling vortex of color, a shortcut, a way to get from one side of the galaxy to the other in the blink of an eye. Starships dive in, heroes get stranded, and entire plots hinge on finding one or closing one. It's a fantastic idea, but is it just an idea? Is there any real science behind it? Are wormholes actually possible? The short answer is maybe, but probably not. The long answer is a lot more interesting. It takes us through the weirdest parts of physics to the very edge of what we know about the universe. It involves strange materials that might not even exist and paradoxes that could unravel time itself. It all starts, as so many strange things in physics do, with Albert Einstein. Back in 1915, Einstein gave us his theory of general relativity. It completely changed how we think about gravity. Before Einstein, we thought of gravity as a force, an invisible rope pulling things together. Isaac Newton's idea. A planet orbits the sun because the sun is pulling on it. Makes sense, but Einstein had a different idea. He said gravity isn't a force at all. He said it's a curve in the fabric of the universe. He called this fabric spacetime. Imagine a giant, stretchy sheet of rubber. That's spacetime. Now, put a heavy bowling ball in the middle of it. The sheet sags. It creates a dip, a curve. If you roll a small marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball. It will spiral in, looking like it's being pulled toward the bowling ball. That, Einstein said, is gravity. It's not a pull, it's matter and energy telling space-time how to bend, and the bend in space-time telling matter how to move. The Earth isn't being pulled by the sun. The Earth is just following the curve in space-time that the sun's massive weight creates. This idea was revolutionary, and it's been proven right again and again. It predicted that light from distant stars would bend as it passed the sun, which it does. They predicted that time runs slower in stronger gravity, which it does. Our GPS satellites have to account for this tiny difference, or their clocks would be wrong and we'd get lost. Our general relativity works, and because it works, we have to take its other predictions seriously, even the really strange ones. And this is where the first hint of a wormhole appeared. In 1935, Einstein and another physicist named Nathan Rosen were playing with the equations of general relativity. They were exploring the weird mathematics of black holes. A black hole is what you get when you put an incredibly massive bowling ball on that rubber sheet. The dent is so deep, it basically becomes a bottomless pit. The gravity is so strong that not even light can escape once it crosses a certain point, the event horizon. While studying the math, Einstein and Rosen found a peculiar solution. It described not just one black hole, but two connected by a sort of bridge or a tunnel. It looked like you could have a black hole with its entrance and, instead of a singularity at the center, a point of infinite density. The math suggested it could open up again into a different region of spacetime. This second opening was what we now call a white hole, a place where things can only come out, never go in. This connection was the first theoretical wormhole. It became known as an Einstein-Rosen bridge. It was a fascinating mathematical curiosity. A bridge connecting two different points in spacetime. It could connect two places in our universe, billions of light years apart, or it could connect our universe to a completely different one. The possibilities seemed endless. Finally, a way to beat the speed of light. The universe has a speed limit, the speed of light. Nothing can travel through space faster than light. But a wormhole isn't about traveling through space. It's about cheating. It's about bending space itself to create a shortcut. Imagine a piece of paper. You want to get from one end to the other. You can draw a line across it, that's the normal way. Or you can fold the paper in half and poke a pencil through both sides. The pencil hole is the wormhole. The distance through the hole is much shorter than the distance across the paper. So, problem solved. Can we build an Einstein-Rosen bridge and start exploring the galaxy? Not so fast. There were some major problems with this original idea. Big, deal-breaking problems. The first problem is that this kind of wormhole is incredibly unstable. The throat of the wormhole, the narrowest part of the tunnel, would pinch off and collapse into a singularity the instant it formed. It's not just that it would close quickly. It would close faster than light. That means not even a single photon, the fastest thing in the universe, could make it through from one side to the other. If you tried to travel through it, you wouldn't pop out in another galaxy. You would be crushed into nothingness at the singularity that forms as it collapses. So, as a method of transport, the Einstein-Rosen bridge is a total failure. It's a bridge that disappears the moment you try to step on it. For decades, that's where the idea of wormholes stayed. A neat mathematical trick, but physically impossible for any kind of travel. It was a dead end. Then, in the 1980s, the idea got a second life. It came from an unlikely source: science fiction. The famous scientist and author Carl Sagan was writing his novel Contact. He wanted his main character to travel to a distant star system quickly, but he wanted the science to be as plausible as possible. His first idea was a black hole, but he knew that wouldn't work. So he called up a friend, a brilliant theoretical physicist named Kip Thorne. Sagan asked Thorne, is there any scientifically respectable way to build a tunnel through spacetime? Thorne thought about it. He knew about the problems with the Einstein-Rosen bridge. He knew it would collapse. So the question became, is there any way to prop it open? Could you build a wormhole that someone could actually travel through? A traversable wormhole. Thorne and his students started working on the math. They looked at the equations of general relativity to see what it would take. What kind of stuff would you need to line the walls of this tunnel to keep it from collapsing? The answer they found was bizarre. To keep a wormhole open, you would need something with a very strange property. You would need matter or energy that has negative pressure. Or, to put it another way, it would need to have a repulsive gravitational field. It would need to be anti-gravitational. Let's go back to the rubber sheet analogy. Normal matter, like a bowling ball, has positive mass and positive energy. It creates a dent that pulls things in. To prop open a wormhole, you need something that does the opposite. You need something that would create a bump on the rubber sheet. Something that pushes space-time apart instead of pulling it together. This theoretical stuff got a name: exotic matter. This is the absolute key to making a wormhole work. Without exotic matter, a wormhole is just a fleeting mathematical ghost. With exotic matter, it might just become a stable doorway to the stars. So the billion-dollar question becomes, does exotic matter exist? Our everyday experience says no. Everything we've ever seen or touched has positive mass and energy. Rocks, water, air, stars, galaxies, it all pulls, it never pushes. It all creates gravitational dents, not bumps. If exotic matter existed in large quantities, we would have seen its effects by now. We would see objects in space being pushed away from each other for no reason. We don't see that. But we've never seen it isn't the same as it's impossible. The world of physics, especially at the tiny quantum level, is a very strange place. And it turns out there is a known physical phenomenon that seems to produce a tiny amount of this negative energy effect. It's called the Casimir effect. Here's how it works. According to quantum mechanics, empty space isn't really empty. It's a bubbling, fizzing sea of virtual particles. These are pairs of particles and antiparticles that pop into existence from nothing, exist for an unimaginably short moment, and then annihilate each other. They're happening everywhere all the time. Now imagine you take two perfectly smooth, uncharged metal plates and place them incredibly close to each other in a vacuum. We're talking nanometers apart. Outside the plates, virtual particles of all wavelengths can pop into existence. But between the two plates, only particles with a wavelength that fits neatly into that tiny gap can exist. This means there are fewer virtual particles popping into existence between the plates than outside the plates. This difference creates a pressure. There's more stuff pushing on the outside of the plates than on the inside. The result is a tiny measurable force that pushes the two plates together. Where does the negative energy come in? The region of space between the plates has less energy than the empty space outside it. It has a negative energy density relative to the vacuum. It is, in a very specific and tiny way, a real-life example of the kind of effect needed to sustain a wormhole. This is huge. It means the concept of exotic matter isn't pure fantasy. It has a basis, however small, in real-world physics. And this is a very big, but there's a massive difference between the tiny negative energy density in the Casimir effect and creating a stable chunk of exotic matter big enough to hold open a wormhole for a person or a spaceship. It's like seeing a single raindrop and trying to figure out how to build a global ocean from it. And physicists have tried to work out the rules for exotic matter. They've come up with something called quantum energy inequalities. These are basically a set of laws that seem to limit where and how much negative energy you can have. The theory suggests that you can have little pockets of negative energy, but they have to be balanced out by bigger pockets of positive energy nearby. You can't just have a lump of this stuff floating around on its own. It seems the universe has a strict budget for negative energy, and it doesn't like you to overspend. If these inequalities hold true, then building a human-sized wormhole might be impossible. The amount of negative energy required would be immense. To create a wormhole with a throat about 1 meter across, you'd need an amount of negative energy equivalent to the mass of the planet Jupiter. And that negative energy would have to be concentrated into a very small space. We have absolutely no idea how to do that, or even if the laws of physics would allow it. It might be that the universe has fundamental laws in place that forbid the creation of large, stable collections of exotic matter, precisely to prevent things like traversable wormholes from existing. But let's be optimistic for a moment. Let's pretend. Let's say we figure it out. Maybe some advanced civilization in the future discovers a way to manufacture and control exotic matter. How would they actually build a wormhole? We're deep into speculation here, but there are some ideas. One idea is to use quantum foam. At the very smallest scales of reality, smaller than an atom, space-time itself is thought to be a chaotic, bubbling foam. Tiny wormholes and bubbles in space-time might be constantly popping in and out of existence, just like virtual particles. Perhaps an incredibly advanced technology could grab one of these submicroscopic wormholes and pump it full of exotic energy, inflating it to a macroscopic usable size. Another idea involves black holes. Maybe you could create two black holes and then somehow bring their singularities together. Then you'd have to thread the connection with a huge amount of exotic matter to stop it from collapsing and turn it into a stable, open throat. The engineering challenges are, to put it mildly, staggering. It would require manipulating gravity and energy on a scale that is far beyond anything we can imagine. We're talking about a civilization that can casually move stars around. So let's continue our fantasy. The wormhole is built. It's stable. What would it be like to use it? What would you see? The movies usually get this part wrong. It probably wouldn't be a wild, psychedelic tunnel. From the outside, a wormhole mouth might look like a perfectly spherical crystal ball or a calm mirrored sphere. It wouldn't have any obvious entrance, it would just be a distortion in space. Looking into it, you wouldn't see a tunnel. You would see the view out the other side. If the other end of the wormhole was in the Andromeda Galaxy, you would see the stars of Andromeda framed by the sphere of the wormhole mouth. The view would be distorted, like looking through a fisheye lens, but it would be there. You could literally look from your backyard on Earth and see a planet orbiting another star, hundreds of thousands of light years away. What about the journey? You'd step through the sphere. For you, the trip might feel instantaneous. There's no real distance to travel through the throat. You're just stepping from one point in space-time to another. But there are still dangers. The same forces that hold the wormhole open could be incredibly violent. The exotic matter would create intense gravitational tidal forces. If the wormhole wasn't big enough, these forces would be stronger than a black hole's. They would stretch you in one direction and squeeze you in another, ripping you apart atom by atom. To be safe for a human, a wormhole would need a mouth that was at least a few light years across. The scale of these things is hard to comprehend, and now we come to the weirdest part of all. If you can build a wormhole, you can almost certainly build a time machine. The two ideas are deeply connected. It comes back to Einstein's relativity. One of the consequences of his theory is time dilation. The faster you move through space, the slower you move through time relative to a stationary observer. This is the famous twin paradox. If one twin stays on Earth and the other flies off in a spaceship at near the speed of light, when the traveling twin returns, they will be younger than the twin who stayed home. Time literally passed more slowly for them. So here's how you turn a wormhole into a time machine. First, you create a traversable wormhole. Let's call the two mouths A and B. They are right next to each other, and they are synchronized in time. If you step in A, you step out of B at the exact same moment. Now you take mouth B and put it on a spaceship. You fly it around at near the speed of light for a while, maybe for a year from your perspective on the ship. Then you bring it back and place it next to mouth A again. Because of time dilation, time has passed more slowly for mouth B, while 1 year passed for mouth B, maybe 10 years passed for mouth A, and the rest of the universe. Mouth B is now 9 years in the past relative to mouth A. So, let's say the year is 2050. You walk up to mouth A. You look through and see the world as it is in 2050. Now you walk over to mouth B, you look through it and see the world as it was in the year 2041. You have a window into the past. And it's not just a window, it's a doorway. You could step through mouth B in the year 2050 and step out of mouth A in the year 2041. You have just traveled back in time. This leads to all sorts of famous paradoxes. The most famous is the grandfather paradox. What if you go back in time and accidentally cause an accident that prevents your grandfather from meeting your grandmother? Then your parents would never be born. You would never be born. But if you were never born, you couldn't have gone back in time to cause the accident in the first place. It's a logical contradiction. The universe seems to be breaking its own rules. How do physicists deal with this? There are a couple of main ideas. The first is called the Novikov self-consistency principle. It basically says that the laws of physics forbid paradoxes. The universe is self-correcting. If you travel back in time to try and change the past, something will always stop you. If you try to shoot your grandfather, the gun will jam, or you'll slip on a banana peel, or a bird will fly in the way. You can participate in the past, but you cannot change it. Any action you take was already part of history. The timeline is fixed and self-consistent. You can't break what's already happened. In this view, there is no free will when you travel to the past. You are just playing a part in a script that has already been written. The other popular idea comes from quantum mechanics. It's the many worlds interpretation. This theory suggests that every time a quantum event happens, with multiple possible outcomes, the universe splits. Each outcome happens, but in a separate parallel universe. If this is true, then when you travel back in time, you don't travel into your own past. You travel into the past of a new parallel universe. You could prevent your grandfather from meeting your grandmother in that universe. The version of you from that universe would never be born, but it wouldn't affect you, because you are from a different branch of reality. This neatly solves the paradox, but at the cost of creating an infinite number of parallel universes. The fact that wormholes seem to inevitably lead to time travel paradoxes is, for many physicists, a strong argument against them. The universe seems to have a way of protecting itself from these kinds of logical contradictions. This is sometimes called the chronology protection conjecture. The idea is that the laws of physics themselves, perhaps in ways we don't yet understand, conspire to make time travel impossible. This might mean that building a stable wormhole is impossible. The very act of trying to create one might cause it to be destroyed by a feedback loop of energy, for instance. So, after all this, where do we stand? Are wormholes possible? The answer is a very unsatisfying mix of yes and no. The geometry is possible. Einstein's theory of general relativity provides the blueprint for a shortcut through spacetime. The math works out, you can write down the equations for a stable traversable wormhole. So, in that sense, they are theoretically possible, they are not forbidden by the known laws of gravity. However, the physics required to build one seems to be impossible. The one essential ingredient, stable, macroscopic, exotic matter with a large negative energy density, appears to be forbidden by the known laws of quantum mechanics. The Casimir effect shows that negative energy is real, but it also hints that nature keeps it on a very tight leash. You can't just create a Jupiter mass chunk of it to prop open a tunnel in spacetime. And even if you could, the energy required would be beyond comprehension. And even if you could get the energy, the fact that it would also be a time machine suggests the universe might have some fundamental rule that would stop you. We are left with a conflict between our two best theories of the universe. General relativity, the theory of the very big, seems to allow wormholes. Quantum mechanics, the theory of the very small, seems to forbid them by making the material required to build them impossible. This is a common theme in modern physics. Relativity and quantum mechanics don't play well together. They give different answers for what happens in extreme situations, like inside a black hole or at the moment of the Big Bang. To truly know the answer about wormholes, we probably need a new theory. A theory that unites gravity and quantum mechanics. A theory of quantum gravity. This is the holy grail of modern physics. Theories like string theory or loop quantum gravity are attempts to do this, but so far, none are complete or proven. A future theory of quantum gravity might show definitively that large quantities of exotic matter are impossible, and that would be the end of the wormhole story. Or it might reveal a loophole, a new kind of particle or field that would allow a wormhole to be built. We just don't know. So, for now, wormholes remain firmly in the realm of speculation and science fiction. They are an exciting possibility, a beautiful idea that comes directly from our best understanding of gravity. They show us how weird and wonderful the universe could be, but they also come with a long list of seemingly impossible requirements. They need a substance we've never seen and can't create. They would require technology that is practically magic. They would threaten to unravel the very fabric of cause and effect. The universe is under no obligation to make sense to us or to make interstellar travel easy. It's possible that wormholes are just a mathematical mirage, a trick of the equations that can never exist in reality. But it's also possible that we are just at the beginning of our understanding. Perhaps one day, a future generation will look back at our skepticism and smile, just before they step through a shimmering sphere into another galaxy. It's unlikely, but it's not quite impossible, and that is what makes it so fascinating.